Oh, Roger, you might be muted.
Oh, thank you, Adam. I appreciate it. I hate when I do
That's
that because I start the whole intro like, "Oh, welcome back, guys," and I'm muted.
oh
Yeah,
yeah,
well,
you're definitely muted. Don't worry, I've gone like 10 minutes when I thought I was sharing my screen on Zoom and I wasn't, so you're good to go.
oh Lord. All right, well, welcome back, everybody. Today is Friday. Uh, our lesson for this morning is going to be on our data structures and algorithms, specifically focusing on recursion. Um, I believe at least half of you guys were a part of Foundations of Programming, so you have some form of an idea of recursion. Um, it can be a little complex to understand, so we are going to take it very slow, baby steps, to see exactly how recursion works before we even try to implement it. But essentially, recursion is the act of a function calling upon itself until it reaches a specific outcome, right? There's two parts that go into recursion. One is the recursion call itself, and then the last one is the base case, right? Uh, and we are gonna do some tail draw today to see how that works. New page. Yeah, so there's two parts to recursion and how it works. And the most common one is the base case, which in other words is kind of like the if statement of when our function should return. And then there is the actual recursion call where the function calls itself to do the solution of what it was made to do. Maybe that's a little difficult to understand, but we can talk about it and exactly what it is, right? So recursion programming is a technique where a function calls itself, right, in order to solve a problem. We mentioned that we do have a base case and a recursion call. I don't see it anywhere in here, but it's a very helpful algorithm because it can be very elegant to use. So it's very clean. It's nice to use. You don't have like complex code, uh, but it can get messy really quickly if done wrong. What that means is, if you don't set your base case properly, what would happen is you would essentially create some form of an infinite loop, which can affect your space complexity because every time it calls itself, it takes up space. But if done properly, it can also increase your space complexity as well as your time, right? So recursion could lead to an increase in time complexity, but as mentioned before, it's kind of a double-edged sword, right? If used improperly, what ends up happening is you might overcomplicate the problem when it could be something very simple, where a simple iteration like a for loop could do the exact same thing. And I say that because um, I have a buddy of mine that is also a software developer, and every now and then we'll do like coding prompts together. Um, and his first attempt at solving a problem is always recursion, and he'll spend about 30 minutes to 40 minutes trying to figure out how to make it work with recursion, just to figure out that maybe it was a lot simpler if he did not do that. Um, let me, all right, continuing where we left off. Yeah, so he'll spend like 30 minutes trying to solve it just to realize that he might have overcomplicated the solution, and it was just easier to use a simple for loop than try to get complex with it. But when you use it properly, it does eliminate a lot of extra code, um, and it can help you with your time complexity, right? Poorly designed recursive algorithms may lead to inefficient time complexity, right? So each recursive call adds a new frame to the call stack, right? And we'll talk about what exactly is a call stack if not done properly, therefore increasing your time complexity. A simple recursion problem, which I use for foundations programming, is using a countdown or a count up function. And we can use this to demonstrate how it works. This method here takes in a number. And the goal of this function is to take this number, utilize it, and print out the number counting down or counting up. As a matter of fact, let's count down first. And as we discussed, there's two things that our code must have. That is the base case. And then there is the recursive call. All right. The base case is what the function used to know when it is ready to return to you the result and no longer continue calling itself, right? So this is the if statement, right? That while statement where we say like while this is this, then continue calling yourself, right? That is what the base case does for our recursive call. It sets a constraint to keep our recursive function from calling itself over and over. For our base case for the countdown, it will be if n is equal to 0, right? So what we are attempting to do with this recursive function is to count from 5 down all the way to 1. But in the event that it reaches 0, then we should stop printing out anything. So our base case sets that condition here. So we say if n is equal to 0, then I just want to return. But while it does not equal to 0, what it should do is call itself. And the way that the recursive function will work to actually do what we want it to do is when we call it the second time, we need to update the argument that's being passed within our function. So initially, when this function starts, it should look something like this, where we pass in a number of 5. It'll run the first time. It'll check, does n equal to 0? It does not. And we can say print n. So the first time this function is called, we print out what the number starts at. Then it gets to this line here, where it calls itself again, but it lowers the size of n, making it 4. So the next time this function runs, it prints out 4. It calls itself again over and over again until it eventually reaches this base case. Now let's see how that looks in a drawing. This square represents your memory of where the call is being held at. The first time that we run this function, it creates a stack. Right, this is the first stack. And this is just the first function that is called. This actually makes it smaller to kind of see this. So this function runs, it prints out 5. Oh Lord. There we go. Prints out 5. It gets to the else statement because 5 is not 0. It calls itself again, but this time it lowers whatever n is. And it creates another stack. Well, what happens to the original function? Who could take a guess? Does it just disappear?
It pauses.
It pauses, right? It almost stops. Why is that?
Because your other function is running that recursive function.
Yeah, it's still running, right? At no point has this function returned anything. So this call almost pauses and stays like on a pending status, right? It pauses because within itself, it called another function that is now running within that function. So this call kind of stays in limbo and it's open because it is yet to finish what it's processing. Because within the function itself, it's running another function, which is a countdown with 4. This function runs. It checks the base case. Do I equal to 0? I do not, so I do not return here. I go into my else statement and I print out 4. So we print out 4. And now countdown 4 reaches the line where it calls itself again. So now this function is now in limbo as well. It pauses and it's still running. And now we have another stack. But within that function, we lowered the size of n one more time. So now n is equal to 3. So we now have 3 stacks. 2 of these are still open. We are now three stacks in. Countdown reaches the base case. It is not equal to 0. So it goes into the else statement. It prints out 3. It goes into the recursive call and opens up another function. And it does this until it reaches that base case. It does not meet the base case yet. So it calls itself again. Countdown of 1. And finally, it gets to a point where it gets to its last stack, right? Once countdown 1 runs, it gets to the recursive call. It lowers n to 0, and it calls that function again. It reaches the first part of the code where it checks the base case, and it sees that it is equal to 0. So it returns. It no longer continues calling itself. And what happens is that this let's change color. This function closes, right? It returns something back to us, right? Because it reached the base case, it returns, right? We're not returning anything specific, so it essentially returns none. But that function successfully finished running, and it returns back the result to what originally called it, which was countdown, where n is equal to 1. Since that returns something, this closes up as well. It returns none back to countdown 2. And it does this all the way back until it reaches the original function that started the recursive call. Therefore, closing up all the calls. Now, why did I put this in a circle? Well, there is a limit to how many recursive calls you can make, right? I don't know the exact limit. I do apologize. But one of the limitations to recursion is how big the items you're working with are, right? For more complex problems, if you try to use recursion, right? If I try to like count down from like, let's say 10 billion, I will probably get an issue, right? Because there's a limit to how many times this recursive call can run. And what happens is when it reaches its limit, we get an error, which is known as stack overflow, where the website gets its name, right? You guys have heard it. right? Stack overflow is the error message that you get whenever recursion dives way too deep within itself and it calls multiple functions and they're all open and it can no longer call another function and it gets an error, right? As you see here, this is a stack, it's overflowing outside of our memory and we can no longer hold it. Therefore, we get an error. This also happens in the event that you don't set a proper base case, right? You essentially create an infinite loop where it keeps calling itself over and over again and it never reaches the condition where they need to close and return. We tend to also use this as recursion. We use an example of pancakes. A circle. Whenever you have a stack of pancakes, oh, Lord. Oh, okay, there we go. When you have a stack of pancakes, right? If you want to grab the bottom pancake out, you can't really do that without doing something to the top, right? You can't just drag it out. And that's how we like to think of our call stacks, right? As our recursive call gets in deeper, we can't close up the bottom stack because there are other stacks above it that still have yet to be taken care of. All right, so this is another way of seeing it when thinking about the recursive calls and how that works, right? The initial stack that starts this entire process cannot be removed until the ones above it has finished what they were intended to do. Let's see that in code. Oop. So we define the function count down, and it takes in a number. And we say if n is equal to 0, then return. Else, I want to print n. And then I'm going to count down, and I edit my number. We can call the function and pass in 5. And just for giggles, let's go ahead and not add the change within our recursive call. Therefore, it never meets our condition. And we see here, I get an error where it says maximum recursion depth exceeded while calling a Python object. So it kept running and it kept printing out n. And it's definitely not 10 billion, but we see here there is a certain amount, right? What if, no, it's fine. Yeah. All right, so it keeps running and running, it keeps calling itself, and eventually it reaches a point where it can no longer call any more recursive calls because it's reached its depth. I'm surprised we didn't get Stack Overflow, but you used to see here in area that said Stack Overflow. Right now, it's just telling you maximum recursion depth exceeded. Right, but that is essentially a Stack Overflow error. Do I have any questions about recursion so far?
Yeah, if you set it equal to a new value, for example, countdown n equals countdown parentheses in the else statement, when does it now take on that value? After they start closing on each other at the very end, and then what does the value look like? Does that make sense?
Are you referring to this right here?
Yeah.
Well, let's see how it looks when we run it correctly. When we actually add a change to the end value, at one point, as we saw within the diagram, it will reach 0, and then it starts returning, right? This returns none, right? So we don't see anything else being printed out here or whatever. The first time it runs, n is equal to 5, right? We pass in 5. This is the first time we run it, and it prints out 5. We get to line 5 and 6, right? We print out 5 here on line 5. And on line 6, we edit the value of n by 1. So then the next time that this function runs, n is going to equal to 4. That's
Yeah,
where,
but if you assign it, if you reassign it right now to, like the way I put in the chat, n equals countdown, parentheses, n minus 1, what will that value be at the end? Will it be what the last iteration was, or would it be whatever the very first one is? Does that make sense?
n equals, oh, I see what you mean. Why are you trying to deliberately break this? Let's try it out.
I'm having an issue remembering it now.
Yeah, I forgot Juan likes to deliberately try to break stuff. I pair programmed with him before.
It still works. Let's run it again because something doesn't save.
No, it'll work, but you're reassigning n every single time. So I'm wondering, when does the assignment take place? When they start closing on themselves, or does the assignment take place immediately after the function gets ran and it reaches a value?
That's a good question. It's going to do it at the very end, right? Because it gets to line 6, and you're trying to reassign something from this function. This function has to run to return something to assign it to n, but it won't return anything until it reaches the last stack, right? So it just goes deeper into its own function call.
So if we're looking at the stack, it looks like how I just typed it in the chat, right? 1, 2, 3, 4, 5 in order. Which value now gets assigned to n? Does that make sense? That's essentially what the question was. I'm just wondering.
On the first recursion call, you don't change anything on n, because this opens up another function, right? It dives deeper within itself, and this initial function stays in limbo, right? It stays open. So this never gets reassigned until the very end, the last time. Once it reaches here, right, on the 5th call that we saw on our drawing, right, once it gets to countdown of 0, then we assign n. Oh no, we don't assign anything here. We return none, right? So this comes back, and it should come back, and because it's returning none.
Yeah, that's where I got stuck. Will it return
N
none, or will it return at the 4?
The first time it's going to equal none. That second time, it'll return okay. Yeah, it'll return none, but we don't see it happen because we're printing it out before we assign it. Right? So although the last function does return none and reassigns n, we've been printing it out every single time. Does that make sense? We printed out 5 before we did the reassignments. This calls itself again, right? The next time n is equal to 4, right? Because we changed n here for 4, but it hasn't been reassigned here because the call opens up again. I'm moving forward with your question because it's a good question, right? But I do want to give you a warning. You might overcomplicate this and confuse the people. But I will answer your question, right? So it won't affect our print statement because we're printing out every single time that we call this function. And at no point does the reassignment ever impact our print statement because we print it out before we try to reassign it. And this doesn't get reassigned until the last stack is called. But by then, we've already printed out the numbers as we need it. Does that make sense, Juan? All right. Do I have any other questions before I move forward? I see Gary has a good toxic trait. All right. So, I talked through recursion with a very simple problem. We'll take it up to level 2. And this time we're going to do the factorial. For those of you that do not know what factorial is, it is essentially the multiplication of all the numbers that combine up to the number you're given it. Let me give you another example using this demonstration here. 5 factorial, right? And what do I mean by factorial? Well, that's the name of the symbol here. Factorial is resembled by this exclamation mark. 5 factorial is equal to the number itself, 5, multiplied by the numbers that came before it. So 5 factorial will equals 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1 equals 120. So 5 factorial is equal to 120, and that 120 is the output of all the numbers from 5 to 1, right? All the numbers that came before 5 multiplied together. 4 factorial is 4, and then all the numbers that came before it, and then so on and so forth for 3 factorial, for 2 factorial, and then 1 factorial. Right? 0 factorial is equal to 1. 1 factorial is equal to 1. All right, so both of these are equal to 1. Right, note that the 0 factorial equals 1. This is important. Right, that's just how the factorial math works. I did not specialize in math, so I cannot elaborate a little bit more on why it equals to 1. But just know that 0 factorial does equal to 1. All right. Now let's see that in code. I have a lot of stuff on my desktop. Ignore it. So we have countdown. Let's go ahead and comment this out. We are going to define our function, which is going to be factorial. And factorial takes in a number. Right. Now, we're going to say, well, first we're going to set up our base call. And our base call, as we mentioned before, this is the condition that lets our recursive call know when it should return back to us. Right. And we essentially, I'll write the recursive call first. What should happen is we want to multiply all the numbers that come before it. So when we call this function, if we pass in 5, we want to multiply 5 by 4, and then multiply that by 3, and then multiply that by 2, and then 1. Right? So the function call, what it should look like is at the very end, when we do reach 1, we need to multiply that by the number that is in the function before that specific recursive call. So it should look something like n multiplied by factorial and minus 1. And we'll break it up a little bit. The base call needs to know when it actually reaches 1 or 0, right? And this is where it comes important of why O or 0 factorial and 1 factorial is equal to 1. So you can establish your base case. So essentially what we have to say, if n is equal to 0 or n is equal to 1, then we need to return 1, right? Because both of these, their factorial is 1. So once it reaches the last part of our call, at any of these, they both have to return 1. If it's not equal to 1 or 0, that means that it probably equals 2, 3, and 4. And that's what we have to essentially multiply. So let's kind of draw it out here, or add some notes here. The first time that factorial n runs, it is going to essentially equal to 5, right? And it will be 5. It's going to check the base call. Hey, does n equal to 0 or 1? It does not. So it's going to move to the else statement. And it's going to say return 5 multiplied by factorial 5 minus 1, right? Because that's what n is. Let's just add n here. N, which is 5, minus 1. This multiplication will not actually happen until the recursive call runs. Right? So we don't multiply 5 yet by whatever this is, because once it goes into the second recursive call, n it will be 4. It's going to get to the base case. It won't meet the base case criteria. So it'll go to line 17, and it's going to be 4 multiplied by factorial 4 minus 1. This also does not run yet, because now we dove even deeper. We called another recursive call. So we'll say something like this, where we say first call. And then we'll say second call. And this is the third call. And this time n is going to be 3. It gets to the base case. It does not equal 0 or 1 yet. So we go into the recursive call. N is now 3. And it's being multiplied by factorial. And that's equal to 3 minus 1. So we go into our fourth call. Now we adjusted n again. So this is going to be 2. It checks the base case, which it does not meet the criteria for. So then 2 is multiplied by factorial for 2 minus 1. And then we get to our fifth call. We subtracted 1 from 2. So now this time, that fifth call, factorial of 1. And now finally, we reach the base case. And it says if n is equal to 0 or 1. Well, it does equal to 1. So this fifth call returns 1. right? Let me see if I can draw here. So this returns 1 back to the original call that called it, which was the 4th call, right? So this ends up being 1. So 1 times 2, right? And then we return this, because that's how we have it set up here on the recursive call. We return whatever is multiplied from these two. So that brings it up back here. So 2 times 1 is 2. So that 3rd call will multiply that 3 that it had in limbo by whatever came back from that function. So 3 times 2 is 6. That returns it to the original one that called it. This is 6. So now it can go forward with the multiplication. We say 4 times 6, which is 24. Quick math. I think it's 24. I hope it is. I don't want to sound dumb. So 6 times 4, 6, 12, 18, 24. 24 multiplied by 5 is, I believe, should be 120 if someone wants to do that quick math. All right, but it essentially gets to its last recursive call, the one that originally started this loop. We multiply 5 by 24. And this is what is being returned to us at the very end. All right, the result of that, which I believe is, I think it is 120. Right? And that's how the factorial works, right? How we are able to grab the product of multiplying everything of the number and the numbers that came before it. Let's go ahead and delete this. And see it at work. Let's print this out. Print. We run the file and we see here that we get 120 back from our factorial function. Thank you, Nikayla. Math hard. Do I have any questions about factorial and how we can use recursion to do it? Okay. All right, this next one, I'm gonna let you guys attempt it before we talk through it. And this is gonna be the Fibonacci. It is in the curriculum. Do not look at the curriculum, so you guys can get a honest try. But the next one is gonna be the Fibonacci sequence. And essentially the Fibonacci sequence is a series of numbers where the next number is the addition of the number of the two numbers that came before it, right? So we start at 0, right? There's no number that came before 0, so it just goes to 1. But the next number that comes afterwards, it's the addition of 1 and 0, right? So we see 1 plus 0 is 1. So our third number is 1. The fourth number is the addition of the last two numbers that came before it. So 1 plus 1 is 2. We see here that the next number is 3. That is the addition of the two numbers that came before it, which is 2 and 1. The number that comes after 5, or after 3, my apologies, is 5. And that is the addition of 3 and 2, which were the two numbers that came before it. And it does that all the way to the very end. Right? Your task is to grab the Fibonacci sequence of a specific number. Right? So essentially, I want you guys to use recursion and figure out what is the Fibonacci of, we'll use the example here, of 55. Do I have any questions about this example? All right.
I have a question.
What was that? Len? Yes.
Yeah. Just because I know this one from when I was taking my programming class. There is a trick to this Fibonacci, isn't there? Like it's a little more complicated of a recursive thing.
Yeah.
Like my teacher told me that. Like my teacher was straight up like, "You're not mathematicians, so just know there is a thing here."
Yes. Let's talk about that real quick.
Because that will
So-
trip people up.
I think I know what you're getting at. What Len is probably referring to is the type of recursion there is. There is two different types. I think there's more actually, but the ones that we would talk about is linear recursion and binary recursion. The difference between these two is the amount of recursive calls that are used. What we just saw is recursion using only one recursive call, right? But you are able to split up the workload by using two recursive calls within your function. And I'm assuming that's what you're talking about, Len.
I think so.
Okay.
So
Well,
I know the formula. The formula you need to do is particular.
yeah, we'll give it an honest try. I'm going to break you guys up into your groups, right? And Len, as you do have previous experience, you'll probably be a good help to your team. So let's give it an honest try. The Fibonacci is the only real other recursive assignment on this lesson, which is why I want you guys to actually attempt it instead of just talking through it and then not letting you guys try it out. So let's go ahead and pause the recording.
Okay, so we defined Fibonacci function takes in n as a parameter. We said if n equals 0, then you return 0, and if n equals 1, then you return 1. And then our those were our base cases. And then our else statement is just we return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And it just keeps doing that until it reaches the number that was inputted. So yeah, it's just adding the two, it's feeding the number that came before n back into the Fibonacci sequence, and then it's adding the two numbers, the number that comes two places before n back into the Fibonacci sequence. And then, you know, we did like so we have a print statement here. So we do 12, and if I run it, let's do this. G. I get 144 there. I don't know if somebody wants to try another number, but that's pretty much what we did.
Yeah, that's pretty good. You know, it's the sequence is going to call itself until it reaches that base case, which is either 0 or 1.
Yeah.
And it does, right? It does, where essentially Fibonacci, the first Fibonacci recursive call on line 8, ends up being 0, and the other one on the right ends up being 1. Well, actually, it's probably the other way around. And then it adds them together, and it just comes back up to its original call, give you the sum at the very end, which is exactly how it's done. Good stuff, Jacob. All right, let's go ahead and move forward. So here is the Fibonacci example. It was in the curriculum. If you guys couldn't find a solution, good job, Jacob, Gary, and Michaela. We went over the call stack and how that works. I showed you the example for countdown, and we broke it down per step. The next thing would be, what if we were doing the factorial, right, earlier, but instead of going down, we were going up, right? So here on factorial, we started with the number 5, right? And we were doing the multiplication downwards into the stack. So 5 multiplied by the results of whatever came back. But what if I wanted to do it backwards, right? Let's kind of edit this real quick to see how it would look like. Maybe we can print, how can we do this? If I print n here, now let's do it up here so we can get the 1. It's still giving me the same thing. Okay, that's fine. Well, when it first starts off, we passed in 5s, so it prints 5. It goes through this sequence. We get 4, we got 3, we got 2, and we got 1, and eventually it reaches this portion right here where n is multiplied. So it does give us that 120 at the very end, which is why you see this. But well, actually, no, you see this one right here because we are printing out the result that comes back from it. That's where that was coming from. I was confused. If we remove this, we should not see that 120 anymore. There we go. Okay. All right. So we see here that in the original sequence that we created, when we got the factorial of 5, I was able to print out what n was to see how it was going from, from a big number to 1 to its base case. But what if we wanted to do that backwards, right? And keep track of the count from 1 up? Well, you're also able to add other arguments within here that we can use as a constant, or not as a constant. We set a default, and then we can use this variable that we established and carry it on throughout our entire recursive call to keep track of other variables that isn't specifically just n. And we can do something like current is equal to 1, right? And when we start this factorial, we would have to edit this a little bit, where essentially we say if current is greater than n, we can return 1. And if not, we should return current multiplied by the factorial. And then we will have to edit this to n, and then current plus 1. Now let's see how that works, and we can break it down step by step. Where can I print this out? I guess I could do it up here. It prints out that last one. Maybe we do it here. Per current. So we can visualize this. There we go. All right. So here we got the factorial for 5, but we did it backwards. Where before we were able to get it from the, starting from 5, and we broke it downwards until we reached 1. We were able to create a variable here called 1. And we use that variable to keep track, right? When we first start, it checks with current, does it equal greater to 5, right? And 5 in this situation is n, right? we pass in 5, n is 5, and we check, hey, does current, is it greater than n? If it is, I want to return 1. Therefore, that means we've reached the end of it. We were able to multiply the way up all the way to the number 5, and at the same time grabbing its factorial. But if not, what I want to do is multiply current, which is 1, by the recursive call of factorial n current plus 1. So the next time this comes in, current, we edit it to be plus 1. So therefore, current ends up being 2, right? Or before, we were keeping track of n and the number that came underneath it and multiplying it. Here, we set a default of 1 to grab the start. And we multiply the next number that comes after adding 1 to that current. All right, so the second time this runs, n is still equal to 5, but current is now 2. Right, so we used a different argument here, a different value to keep track of the factorial process, and all we're using n is to figure out when we've reached that point. When is current equal to the number that we are trying to grab the factorial for? So n didn't have to do anything. We used current instead to do the multiplication process of it. So it's still fairly similar to the first one. The only difference here is that we added a second argument here that we were able to keep track of. Notice that that argument has to change within the second and third and fourth and so on and forth for the recursive calls to do anything. A common mistake here is trying to add a variable within your recursive call to keep track of something, but you don't pass it in within your next recursive call. So what I mean by that, if you were to do this, right, and you don't, I'm sorry, not this. If you did this right here, if you say current multiplied by factorial n, what's going to happen the second time this runs, current never changed, right? Current is not being tracked with any of the changes that are being made. So every time this runs, current will always be 1. And that's one of the common pitfalls of using a second value to keep some form of counter, right? Or keeping track of values that you want to use for your function, right? So any value that you're using, like if you had a method where you're trying to keep count of how many times something appears in your list, if that counter isn't being added into the recursive call every time you call it, then that counter will always stay the same. All right, so just one thing to take into consideration. All right, so comparing recursion and iteration. Right, iteration being your for loops, your while loops, right? When should you use one over the other? Well, first and foremost, I would take into account the readability and then stack usage. I say readability because, as you've already noticed when talking about recursion this morning, it can be a little confusing if you don't understand the concept of recursion. And that's probably one of the reasons why it's not really used too often in the real world, right? Not many people do it. I've asked my other software developer friends who've been doing this for years. They have yet to use recursion in any real life problem. It's not something that is commonly used. It's a little intimidating because it can easily go wrong. And not many people have a grasp on the concept where they feel confident enough to actually implement it. So you can really, mess that up if you don't understand the concept. Or if others struggle with recursion, it can be a little difficult to read. But if done properly, it is a very elegant approach. And it can handle your code where it doesn't look like a jumbled mess of just a bunch of for loops and while loops, right? The next one is the stack usage. As you saw when I made that infinite loop, it did go through the recursive call multiple times. We saw probably maybe like 100, 150 calls that were made. But after a certain point, it stopped and it said it exceeded its maximum space. Right? We got that Stack Overflow issue. So, the stack usage. So if you use certain values where you're going to have an excessive amount of calls, recursion might not be something that you want to use. I'm not too familiar with tail recursion and it's not in the curriculum, so we won't talk too much about it, but this is a way to optimize your recursion. But I'm not going to try to pretend like I'm a subject matter expert on something that I have not used often myself. Yes, Owen.
So for about stack usage, so for the example of the Fibonacci sequence, when you reach that stack usage limit, would you be able to nullify that somehow, or is that just the point where you start using a for loop?
What do you mean by nullify it?
So like the stack overflow, like you said, I don't remember what factor of the Fibonacci sequence you told us to do initially, but we had to cut it down to 12 because we're going to run into stack overflow errors.
Yeah, I think
Would you be able to?
the factorial for like 55 was somewhere around 100 and some million or something like that. And I didn't want you guys to get into any kind of issues on optimizing it. Also, it's too big of a number to try to use recursion. It would just be a slow process.
So that's because we're doing binary recursion. So technically, that would be like a nested for loop if we're like comparing apples to oranges. Is that why?
In a sense, yeah, in a sense. That's a good question, Owen. But yeah, not very ideal for big pieces of data. It just takes too much time, right? And it takes too much space.
Okay.
So for simple stuff, it can be very useful. The comment.
So to answer my question, if it's or if it's going to be a pretty high number, just use a for loop.
Correct. Right. That's when you make the call as a developer. Like, is this even going to be optimal to use if it's going to take a long time or a lot of space? Yes, you would go into a normal iteration.
Yeah, iteration versus recursion is the thing. Recursion, I think, is faster but takes up more space, and so it's all about time. I think a lot of times recursion is used when you're going through trees or like dictionaries where you know the depth and you understand that it's not going to go past n, which is just some really large number. And when you have a good idea of how deep you're going to go, the speed for space can be said. Again, searching trees. Think about a dictionary. Every time you type a letter, like A, T, and the thing has to go through and figure out what all the A's and T's are. Maybe a space where that may want to be used.
Gotcha.
By default, Python sets a recursion depth limit to 1,000. And that's when you will get your recursion error, is what I'm finding.
Yeah. I would imagine if you're using recursion and because you care about the benefits of recursion, you know your system very well, right? And have a lot more knowledge. I would go with what Roger said originally. I would not just recursion. Although someone may in an interview want you to explain. I think the Fibonacci and the two things today are the ones you want to know for when you go into an interview, because it's an easy question just to understand if you understand the concept and see what's going on and how you talk through a problem. And that is definitely one that I've heard people like. They asked me the question and I totally froze.
That brings me back to my, I guess, previous question. So, or not really, but is the time complexity of just a simple recursion call compared to a binary recursion call different? Would the binary recursion call be like a greater time complexity? You're muted, Lynn.
I don't know enough about it. Like Roger was saying before, this is where you learn these things in school and you go over them and you have a couple classic problems and then they leave it for you to discover when you got into the real world. And like Roger said, very few people use them because it often is easier to use recursion. Or sorry, it is iteration. So it's a time, it's a speed versus space thing. And so to put it on an arbitrary like question right now, I don't think it's worth that. You know, in the job,
Gotcha.
in the moment, the people who you're working for should understand the system, know what they're doing, and you can have that conversation.
From what I'm tracking, recursion is a time complexity of O of n, right? And I believe so is the space complexity, because for, as you see here, when we did like the countdown, right?
Yeah.
We
What
had a
about
count.
binary recursion though? Is that
I
different?
that should be, it might be O of n as well. I'll have to Google that real quick if you like for me. But by default, recursion is O of n, and so is space complexity. Is binary recursion O of n? We can look it up. It's O of 2n, so technically it is O of n. It's what it says, right? So binary recursion still O of n. Does that answer your question, Owen?
Yeah.
And once again, back to the space complexity, same concept, right? If we have a number which is 5, right? How many call stacks is that going to open up? 5, right? Going back to that countdown function that we're using. If we were counting down from 5 to 1, then we would have to do 5 stacks, right? So 5 calls in total. What does that mean? Well, as the size of our n, our number, increases, so does the amount of stacks, right? So space complexity is O of n as well. Make sense? Awesome. Quan's over just chugging that mason jar. All right. That's going to conclude today's class. I'm going to give you guys from now until our stand down. Go ahead and stop the recording.